What happens when a giant planet like Jupiter is struck by a massive comet? In 1994, the world witnessed a cosmic event so powerful that it shook our understanding of planetary defense. The Shoemaker-Levy 9 impact view of Earth, enabling powerful telescopes such as Hubble to look at a gigantic dark spot on Jupiter as it occurs. Jupiter rotates quickly with days lasting only 10 hours, as opposed to what you may assume larger planets have, shorter days than smaller ones. The impact of the comet caused shock waves which rippled through Jupiter's thick atmosphere at the speed of 4,450 ms, and all this just from the first impact. Within 6 days, from July 16th to July 22nd, the comet's fragments bombarded Jupiter, the largest one. On July 18th, when fragment G impacted, its impact alone caused a blast 600 times more energetic than the entire nuclear arsenal of the world, leaving an immense dark spot 1 Earth diameter. Then, however, as dramatic as the first encounter was, the comet's tail proved to be equally worthwhile. By examining the debris clouds, scientists gained a unique glimpse into Jupiter's atmosphere and its activity. In addition, they gained an unever-seen glimpse of Jupiter's makeup beneath the heavy cloud tops, as spectroscopic measurements were able to discern material which had been thrown aloft by the comet's collision. They found diatomic sulfur and carbon disulfide and heavy metals such as silicon, iron, and magnesium. Interestingly, they also found large quantities of water, something they weren't necessarily looking for. In fact, one of NASA's Juno spacecraft's main goals is to find out where this water is concealed in Jupiter's atmosphere. However, one of the more ominous consequences of the collision was the discovery that giant celestial bodies would still impact planets. One school of opinion proposed that large comet and acid collisions had been much more common in the early days of the solar system, but Shoemaker-Levy 9 demonstrated that highly catastrophic collisions were still to be expected had it occurred by accident, and we observed a very rare event. Or does it occur more frequently than we believed? Remember, we've only had the technology to observe this type of occurrence. Within the last 80 or so years, if a comet as big as SL9 were to collide here on Earth, it would result in the destruction of most life on the planet. This had a huge impact on our collective psyche, as anyone who lived through the 90s will recall. It was also an alarm for NASA and for some of the different defense agencies. Before SL9, the phrase planetary defense did not exist, but in its wake, NASA began the mission of tracking near-Earth objects, or NEO, with the purpose of detecting up to 90% of asteroids within our celestial neighborhood larger than 1 kilometer in diameter. Having done so, NASA is now firmly on its way towards locating asteroids larger than 140 m. But before you lie awake all night, anxious, take note that these occurrences are certainly uncommon, and there is possibly one other's timing into SL9's collision. You understand Jupiter is a huge planet which has a strong gravitational force, and as it is also one of the outer planets, some scientists now believe it could be a kind of cosmic vacuum cleaner. We do know that Jupiter receives about 2,000 to 8,000 times the number of cometary impacts that Earth receives, so maybe one of the reasons we have extinction-level impacts are that rare here on Earth is the fact that Jupiter had been attracting this type of comets and asteroids. This argument has even found its way into the rare Earth hypothesis, which is the idea that Earth is home to a distinct set of conditions, in the absence of which the evolution of high-complexity life would be impossible. Not everyone is sold, although, and in any case, was still far from demonstrating it. So although we may not have the precise chances of a huge comet or asteroid colliding with the Earth, the effect of SL9 on Jupiter has indeed enlightened our knowledge of these occurrences further. It was, however, indisputably a thrilling moment that subjected watchers to one of the greatest action sequences ever seen with human vision. Perhaps someday we might get to witness something larger, but hopefully from not quite so close as there have been other explosive occurrences such as the 2022 Tonga volcanic eruption, but for the time being, the champion is obvious. The largest explosion on a planet ever seen is Shoemaker-Levy, and by comparison, the competition is a drop in the bucket, while the planets receive plenty of the attention in school and by space agencies. There are smaller, less known worlds in our solar system that are just as interesting. 4 of them are known as the Galilean moons, Jupiter's 4 largest moons. Considering they are so close together, they are fascinating because they are so different. You have a volcano moon, a moon that boasts one of the best odds of harboring life out of any place else that we have any knowledge of, largest moon in the solar system, and a scarred old moon whose surface can be traced back to the earliest days of the solar systems. In this video, we will take the special worlds individually and dive deep into what makes each one so special. By the end of this video, I'm certain you'll see why they will be the target of 2 missions dedicated from both NASA and ESA. We'll begin with the innermost moon, Io. Let's learn about the background of Io a bit better. Jupiter has 79 moons that we currently know of. There's a few orbiting in close proximity to the planet around the planet's rings. After that are 4 big moons referred to as the Galilean moons, named for Galileo, who discovered them in 1610 from innermost outwards. These moons are Io, Europa, Ganymede, and Callisto. Beyond them are the irregular moons of Jupiter, all of which are much farther out than the prior moon Io orbits, extremely close to Jupiter, only 350. 0 kilometers above Jupiter's cloud tops. This means from Io's surface, Jupiter would look 39 times larger in the sky than our moon. Io orbits Jupiter in only 42.5 hours compared to our moon's monthly orbit. At certain points in its orbit, the tidal bulge on Io is believed to be up to 100 minutes. This effect is analogous to what happens on Earth with the ocean tides being produced by the moon, though on Earth the effect is greatly lessened, the tides only typically changing perhaps 2 meters between high and low. Io is receiving 300% more tidal force had influence put upon it compared to our moon upon us. Due to its nearness to the largest planet in the solar system, Jupiter and other large moons in the system don't permit the moon's orbit to be any less. Excentric, meaning Io isn't going to have any respite anytime soon. A day on Io is the same as its orbital motion, which results in the fact that Io is neatly tidally locked to Jupiter, just like we're able to see one face of our moon from Earth. Only one face of Io can ever be seen from Jupiter. Io is a fairly large moon, even though it is the second smallest of the Galilean moons. It is roughly the same size as Earth's moon and has a comparable density, meaning it has roughly the same amount of gravity, but interestingly, it does have the highest density in the solar system out of any other moon. One of its many distinct characteristics is that it is made up of predominantly silicate rock and iron, the same as the terrestrial planets, and our own moon, compared to most other large moons in the solar system that are made of water ice and silicates. Io, in fact, has the least amount of water of any known body in the solar system. Its core is likely to be made of iron or iron sulfides surrounded by a silicate-rich mantle, and crust. The core is not thought to be convex. Though as no magnetosphere has been detected around the moon, the mantle ice is thought to be liquid close to the crust and is a minimum of 50 kilometers thick. This is where all of the volcanism is created, which gets us to potentially the coolest thing about Io, the hundreds of gigantic volcanoes scattered all over its surface. Prior to the 197s, we didn't really know anything about Io at all, though telescopes were beginning to detect indications that the moon was dry and that it might have a sulfur surface. The first mission to observe Io in any form of detail was Pioneer 11, though the quality remained not too good. What it did reveal, though, is that Io consisted of silicate rock and not water ice, and that it possesses a thin atmosphere. Pioneer 10 was also intended to get some close-up photographs of Io, but this was lost because Jupiter's radiation jammed the onboard command system. The radiation Pioneer 10 encountered was 0 times more powerful than the highest radiation near the Earth. The subsequent missions to Jupiter were the Voyager 1 and 2 flights. In 1979, Voyager 1 flew by just 20,000 kilometers away and managed to take some great close-ups of Io's surface. What it encountered was an outstanding landscape full of bright colors and a complete lack of impact craters. It encountered mountains higher than Everest and volcanic basins, hundreds of kilometers wide, and what appear to be lava flows. Most striking, however, was the sight of plumes originating from the surface. This confirmed that Io is actively volcanic, and it is still the first and only location this has been visibly observed off Earth, excluding cryovolcanoes. Voyager 1 also verified that the surface of Io is blanketed in various sulfur frosts. This is what makes Io so many breathtaking colors. It discovered that it is these sulfur substrates which prevail the atmosphere. 4-2 also observed Io in July of 1979. but was considerably farther away at 1 million kilometers, though it still observed 7 of the 9. Plume's Voyager 1 observed in March that meant those volcanoes had probably stayed active over those 4 months. The really interesting pictures resulted from the Galileo spacecraft that reached Jupiter in 1995. The spacecraft was not particularly built to examine Io, but it managed to obtain some of the highest resolution pictures we currently have of its surface. Unfortunately, though, Galileo never operated at full capacity because it had fairly significant mechanical failures, which means we might have had even better pictures if it had been in full working condition. What it was able to capture, though, were plumes of lots of volcanoes, and confirming volcanoes were erupting in sulfur and silicate magmas just like we have on Earth. Except the magma on Io is also magnesium-rich. The surface of Io is spectacularly colored. The yellow PLEs consist of predominantly sulfur. The white regions are predominantly fresh sulfur. Dioxide frosts at the poles. The sulfur is radiation damaged that can be observed since the poles look redder than the planet elsewhere. The colors of red are the residues of volcanic plumes that extended hundreds of kilometers high. Io, the most prominent deposit, is from the volcano Pele, unfortunately an inactive volcano when Galileo was present, but Voyager 1 could observe a huge plume when it flew by. In this photo, this plume stands 300 kilometers high and 200-kilometer broad, in other terms about the size of Alaska. Interestingly, though, the origin of lava flows on Earth tend to be the depression you would usually find at the top of volcanoes, but these depressions are not present on high summits on Io instead. You have these lava lakes with high walls. On the exterior here is Loki, the biggest volcano depression, only 200 kilometers in diameter. These legs are straight tied to the lava reservoir below, but typically do have a thin solidified crust on top on average. Loki emits 25% of the average heat output of Io, but at times the crust on the lava lake collapses back into the lake and causes Loki to emit 10 times more than normal heat. This can particularly be observed in one of Io's other large volcanoes, Tassa. Usually this region appears as such, but here the crust is observed sinking into the lava lake in this picture where only white is seen. The radiant energy from the lava curtain was so strong that the camera could only capture white in 2007. New Horizons utilized Jupiter as a gravity assist to reach Pluto. It also took advantage of the situation to test its equipment. It trained its lens on Io during its flyby, and what it observed was wonderful to share. The volcano I just referred to was erupting fully, and the plume was visible hundreds of kilometers above Io's surface. You can also observe smaller eruptions surrounding the moon. I have to say this is one of the most stunning things that I've ever seen of space, even though the volcanoes tend to be flat. It also has some extremely tall mountains, the highest one reaching 18 kilometers tall. These mountains tend to be completely by themselves, not as part of a ridge or a range, although most are not volcanoes. Lava lakes are found near them, indicating there are faults in the crust near these mountains. Another of the unique aspects of Io is that it interacts with the magnetic field of Jupiter. Jupiter possesses a very strong and very large magnetic field, and Io goes in orbit through some of the strongest parts. The peculiar thing concerning this interaction is that when particles of some of Io's thin atmosphere and eruptions are carried off into space, these particles drift around in orbit about Jupiter in what is referred to ASA neutral cloud. This cloud can stretch way beyond and behind the orbit of Io, but also around Jupiter is something called a plasma torus, a donut of ionized particles that follows the Jupiter rotation of magnetic field. The plasma torus rotates much faster than Io's orbit at 70 kilometers a second versus IIO 17 kilometers a second. Orbital velocity Io circles right in the center of it, with the torus bombard particles bombarding the particles in the neutral cloud, stimulating them to higher energy levels. These recently ionized particles supply the torus drawn in by the magnetosphere's magnetic field lines. These particles are lost from the neutral cloud to the plasma torus at a rate of roughly 1 ton of matter per second, which significantly makes Jupiter's magnetic field larger. In reality, if it were visible, Jupiter's magnetosphere would be roughly the same size as the Moon. In our sky, Io's action on Jupiter does not stop there. Jupiter's magnetic field lines cross by Io couple, Io's atmosphere, and Neal cloud, to Jupiter's polar upper atmosphere by creating an electric current called the Io flux tube. A flux tube is essentially a collection of magnetic field lines. The Sun has these between sunspots, and it's highly visible on the Sun due to the charged plasma that moves between them. Io's flux tube leads to an aurora trail around Jupiter's poles. This is the flux tube from Io colliding with the upper atmosphere of Jupiter. Aurora are also observed on Io, though they are not simply restricted to the poles. The various colors depict the various particles ionized. Green is sodium, red is oxygen, and blue from sulfur. Europa, one of the most thrilling moons in the whole solar system. It is a lovely world abounding in mysteries. This is the very first close-up picture of Europa captured by the Pioneer probe in 1973. Since then, we've had the Voyager and Galileo probes visit the moon, and with each journey, Europa has never ceased to amaze us. We are still yet to solve a great deal of Europa's mysteries, but there are numerous things that we are beginning to put together. Let's first of all examine where Europa sits within the Jovian system. Europa is the second smallest of the 4 Galilean moons, though it's still the 6th largest moon. Within the whole solar system, just behind Earth's moon, with a diameter of approximately 3.00 km, Europa takes 3.5 days to orbit Jupiter. Once 3.5 days is an interesting bit of news. First 3 of Jupiter's Galilean moons, Io, Europa and Ganem, are in an orbital resonance of 421. This is because they exert gravitational pull on one another. Orbital resonance and the continual gravitational pulling from the other moons prevents the orbit of Europa from ever becoming fully circular. Because of Europa's slight ecliptical orbit, the size of the gravitational force upon it from Jupiter grows and diminishes as it orbits. This causes tides that stretch its surface. These forces are considerable since they play a huge role in the appearance of the moon, as well as what occurs beneath the surface. Europa's surface consists mainly of water ice. As you can see, it appears very striking and unique thanks to these continuous long fractures and cracks. These are referred to as linear, which means lines in Latin. These linear can be merely 1 to 2 kilometers wide, but go on for thousands of kilometers along the surface of the moon. We don't know how and why these linear are created at the moment, but the most probable theory is that with the crust being pulled apart due to tidal flexing, warmer stuff from beneath fills in the gap in a manner consistent with the ocean ridges on Earth. In this photo taken by the Galileo spacecraft, you will see some dark brown spots. They are extremely small, only some 10 kilometers in diameter, and they are referred to as lenticula. They are also thought to be created by the upwelling of hot, less dense material to the surface, either by pushing the currently existing crust up or by breaking through entirely should the underground material have broken through. What we can then observe are these unusual terrains, known as chaos terrains. They are actually rough patches surrounded by a quite smooth surface. These areas are to be soft and potentially contain important information about what is below Europa's surface, which we will discuss later in the video data. From Galileo also suggested that Europa's equator could be covered in icy spikes called penitentes. These vertical cracks may be up to 15 m high and will have formed from direct overhead sunlight on the equator. Interestingly, penitentes are found on Earth too, in dry regions at high altitudes, although nowhere near as large as on Europa. Despite being roughly the age of the solar system, Europa barely has any craters. Europa has less than 50 major craters, whereas the Earth's moon has more than 5,000 craters with a diameter above 25 kilometers. This indicates that Europa's surface is constantly changing, and reforming models suggest that Europa's surface is only about 30 to 180 million years old, which is very young. In geological terms, additionally, Europa's icy surface is the smoothest surface of any known solid celestial object in the entire solar system. Its icy crust also has an albedo, or light reflectivity, of 0.641. Of the highest of all, the moon's Europa's albedo makes it 5 times brighter than our moon. The surface is bombarded by a constant and intense blast of radiation from Jupiter. The radiation level at the surface of Europa is equivalent to a dose of about 400 mZ per day. Exposure to radiation at that level would be enough to kill a human in a single day. The reddish-brown color spread across the cracks and fractures of the moon is believed to be due to salt and sulfur compounds mixed in with water ice, and then modified by Jupiter's radiation. A recent study from JPL suggests that Europa might even glow in the dark. Energetic ions from the radiation passes through the surface, which would excite molecules below, which would cause them to emit energy. As visible light, sadly, we cannot see Europa's dark side from our home planet, because we're between it and the Sun all the time, so we are going to have to wait until the future missions to Europa before we will be able to show this radiation coming. From Jupiter plays an important role in Europa's atmosphere too. Europa possesses a highly gossamer atmosphere made up mostly of oxygen and similar to Earth. The oxygen on Europa is created by radiolysis, or in other terms, the radiation bombarding of the water ice surface, splitting the H2O up into oxygen and hydrogen is lost Europa's gravity altogether because it's so light, while much of the heavier molecular oxygen remains. The hydrogen and oxygen that are lost, Europa's gravity form a dispersed neutral cloud which follows the orbit of Europa around Jupiter. In 2012, the Hubble Space Telescope discovered plumes of water vapor around erupting from Europa's south pole. This image suggests that the water plumes rise up to 200 kilometers from its surface. In 2018, astronomers found additional evidence of water plume activity on Europa when they re-examined the Gallo data with a new analysis method. A dedicated mission examining these plumes also allows us to learn what's in the moon without landing on it, because whatever might be beneath that hard ice surface is perhaps the most interesting aspect of Europa. There is going to be an ocean worldwide between a rocky Manley Andes crust, the initial clue that this incredible ocean world was concealed beneath its surface was given by the Voyager and Galileo probes in 1979 and the late 1990s, respectively. Between these missions, there was a sudden change in the magnetic field of the moon, which is impossible unless there is some electrically conductive fluid beneath its surface. Europa's crust also shows that there is a liquid layer under it as it spins with an angle of 80 degrees, which cannot be the case if the rocky crust and crusting mantle were mechanically bonded. Rather, it is possible that the crust is floating on the ocean, and it is thought to complete one full rotation around the moon in a period of 12,000 years. The fact that this ocean is not being attached also accounts for the abundance of linear on the surface. Tidal flexing would make linear appear at certain points on Europa, not everywhere. However, because the crust's position varies with time in a given spot, never remains in the same position for long. Therefore, why increasingly more linear take shape. Europa is 780 million kilometers away from the Sun, which is 5 times farther away than the Earth that makes the sunlight around 25 times weaker here. As a result, Europa, or any other moon in the Jovian system for that matter, receives little if any heat from the Sun, so not surprisingly, it's cold enough here that the surface is frozen. In fact, Europa's surface temperature averages around 60 degrees C at the equator and 220 degrees C at the poles, retaining Europa's icy crust as unforgiving as granite. Yet tidal pressure presses applied to the moon as it orbits Jupiter heats Europa's interior. So geothermal process from the interior should maintain the subsurface ocean liquid. This ocean is thought to be beneath only 15 to 25 kilometers of solid frozen crust. The ocean itself is likely to be around 60 to 150 kilometers deep. Interestingly, Europa is merely 1/4 the diameter of Earth, although it may contain twice as much water as all of Earth's oceans combined. What's most interesting about Europa's ocean is that scientists believe that it is in contact with Europa's silicate rocky mantle. This makes Europa's ocean as suitable environment for life as we know it to exist. We believe that life requires water, minerals, and energy to create, and Europa appears to have all those needs. From the data we've seen so far, scientists are very confident that this ocean not only exists, but that chemical reactions can occur there, and that there is sufficient tidal energy warming the core. That geothermal activity could be present on this ocean's bottom, as we've seen on Earth. Whole ecosystems can thrive in such regions away from the light of the Sun. So for now, one of the most likely places we can actually see life beyond Earth now, NASA's Europa Clipper spacecraft is to be launched in 2022 and is set to arrive at the moon. By the end of the decade, it is to conduct over 42 flybys of Europa. ESA is also developing their own spacecraft named JUICE, or Jupiter Icy Moons Explorer, that will study Jupiter and 3 of its biggest moons. Ganam, Callisto, and Europa. JUICE is also due to launch in 2022 and is also set to make it to the moon by the end of the decade. These probes are tailored to study Europa's water plumes and atmosphere. NASA also has a Europa lander mission planned, but this mission is about to send off after the Europa Clipper mission. These missions will make us learn more about Europa and hopefully validate the response to the most intriguing question of all: does it and can it harbor life? At least these missions will allow us to have a new view of our solar system and learn how it works. So there we have it, almost anything you could want to know about the fascinating world of Europa Ganam, the third of Jupiter's Galilean moons, the largest moon that we know of, and home to the largest water ocean in the solar system. But there's something else that sets Ganam apart from anything else we've seen before. This Jovian giant contains an intrigued mystery buried deep beneath its surface. There are 79 moons of Jupiter, and Ganam is the third of a group called the Galilean moons. Ganam is the biggest of these 4, with a whopping diameter of 268 km for comparison purposes. This is 0.41 times the diameter of Earth's and 1.02 times larger than was previously considered to be the largest moon. Titan seemed larger, as it was due to its dense atmosphere that extends hundreds of kilometers. And so, from fiery Io to the icy mysteries of Europa, we've only begun to uncover Jupiter's hidden worlds. But the story doesn't end here. In Part 3, we journey deeper, where Ganymede and Callisto reveal secrets unlike anything else in the solar system. Thanks for watching.